All right, fantastic. Thank you very much for this invitation. Thank you, Ed, for the very kind invite. I have to say I'm incredibly humbled, just a little bit nervous, but more than anything else, extremely excited to be talking about a little bit about what we do for what I call emerging approaches for reducing concrete CO2 emissions. Loud and clear at the back. I'm assuming that means I'm good to go. Okay, so I want to tell you a little bit about myself before I started talking about my research. So I come from, to laugh and tell people about it, I say a small town in India, but it's like 12 million people or something. It's called Hyderabad. I did my master's. Like CO2 emissions. I'll tell you again in a minute exactly how much, but maybe think about the answers to these numbers.
They weren't hearing you through that, so they're hearing through here.
Okay, so should I just around here?
Yeah, they can hear my head.
Okay, sounds good. So let me put this also here, and maybe I'll carry your iPad around if I have to. All right. So think about these numbers: how much we make and how much it contributes to global CO2 emissions. Also, it's not really possible to replace concrete with any other material, or at least it's really, really tough to do so. And you can make concrete using the simplest ingredients, and it's made and used absolutely everywhere. Okay, fine, but do you need a PhD? Do you need a $3 million equipment to work on? Pretty simple material, right? And the answer is kind of no, it's actually an extremely complicated material. And that also surprises some people, because at the end of the day, it's cement, sand, stones, water, and some other stuff. What can be so complicated about cement, sand, stones, water, and some other stuff? Well, so actually, it does become pretty complicated because it's a composite material. There are seriously complex interfaces where the chemistry becomes challenging. And there is very significant particle and phase heterogeneity, which complicates matters one more bit. And again, this is all taken from my class slides, but I tell folks that concrete is like cooking, pasta specifically. So, maybe at the end of your exams, you go back and you make some pasta, but it's probably a pretty simple pasta because you're tired, you've had a long day. Maybe you put some noodles, a little bit of meat, and that's probably it. But maybe, family's coming over, you want to celebrate, you make a much nicer pasta. Maybe you put veal in it, maybe you put a bunch of spices in it, maybe you put some really nice cheese in it. Both of these are kind of the same thing, but there's a huge difference in the quality and the cost of both of these pastas. Concrete is exactly the same. So that other stuff that we talk about actually has the ability to completely change the properties of the concrete. So you get a very wide range of strength or workability or things like that. So it's actually, there's a lot of different things in concrete. And you have very significant interface and heterogeneity, which makes it complicated enough. Okay, in the simplest terms, what is it? In the simplest terms, it's about 70% of it is sand and stone. About 10 or 12% of it is cement. And about 20% of it is water. This is by volume, by mass. The things are just a little bit different. Specifically, the mass of the water is significantly lower because of density differences. But in a very standard concrete, you have maybe 12% of cement. So and what does actually the cement look like? So I know this is echoing. the cement actually is, in its simplest terms, a mixture of calcium silicates and calcium aluminates. So tricalcium silicate, tricalcium aluminate, and dicalcium silicate and tetracalcium aluminoferrite. These calcium silicate and calcium aluminate phases, this mixture of them, is probably the simplest formulation of cement. So now let's talk about CO2 in concrete. So the numbers I promised I tell you about 2 minutes ago, we make about 20 billion tons of concrete every year. And that is an absolutely massive number. And it contributes about 7% of global CO2 emissions. So the concern, I mean, that a lot of people have is that, hey, concrete is extremely environmentally unfriendly. And this is true. But this is largely because we make 20 billion tons a year of it. If you look at the numbers itself, concrete, I mean, the CO2 emissions of concrete are about as low as it can get. In terms of building materials, the only building materials with lower emissions than concrete on a mass basis are probably straw and stone, right? Cement does have about 10 times the emissions of concrete. And this is interesting because it's only 15% of the concrete by mass, but it's actually responsible for about 90% of concrete emissions. So there's curves like this and figures which are very common in literature, but if you look at embodied CO2 and embodied energy, again, concrete is near the lowest. You can put in 3 dimensions how the cost looks, and again, concrete would come to one of the lowest numbers. So we clearly have a material that's actually very low embodied CO2, it's low embodied energy, and it's pretty cheap. So then the fundamental challenge here is basically just how can we reduce the cement or replace the cement with something else? That's the key to reducing concrete CO2 emissions. And this could be just a small replacement of the cement, a complete replacement, or different materials that are new cements. We'll talk about some of those technologies. There are many mandates about concrete CO2 emissions. And these mandates or these roadmaps, etc., ask that emissions be reduced by about 40% by 2030, and you go carbon neutral by 2050. This is pretty common. I mean, there's so many of these that there's a little bit of variation, but these are pretty standard numbers. So I'll go over several of the strategies, starting with the most standard ones which are already used, to really new or different strategies. I don't know. So this seems to be echoing just a little bit. I don't know. Just turn this off?
Yeah, let's just turn that off.
Okay. All right, so then I just put this. I guess I'm loud enough. All right, I was just joking earlier that hybrid is the worst. I don't know, maybe we mute here or
We need to mute that one. Are you logged into Zoom as well, or no? Just, okay, try it now. Okay, this should be good now.
Loud and clear? We'll take it as it goes. All right.
Yes, it's
so,
good.
Okay, fantastic. Thank you. All right. So what I was talking about was, just to, concrete is pretty environmentally friendly, except we make 20 billion tons of it. Should I still be carrying this with me? No? Everything great? All right, fantastic. So yeah, we make 20 billion tons of it, so pretty environmentally unfriendly, but if we can reduce the cement content, we're in great shape. So where are the emissions coming from? So cement production is actually very simple. I mean, or at least there's been so much research and optimization done on it that's pretty simple. You take limestone, clay, or other materials, and you heat them up to 1500 Celsius. So if you heat limestone to over 900, typically that limestone will decompose and you lose the CO2. And you know exactly how much CO2 that is. It comes out to 44 grams for every 100 grams of calcium carbonate. So about 60% of the emissions just come from this limestone decomposition step, right? it's not so much that you heated the cement. That is maybe 25-30% of the emissions. The remaining emissions are because of crushing, but 40% are just because of heating and crushing. But the 60%, right, is simply because you use limestone as your feedstock. So one of the most obvious ways now of reducing the emissions is to reduce the amount of limestone in cement production. And a very recent technology that has it's 10-15 years old, but technology that has really taken off is what is known as Portland limestone cement, where you add about 5 to 15% of the limestone. Instead of adding it during the heating, you add it post-heating, and this results in about 4 to 12 or 13% of emissions reductions. So as we mentioned, the most environmentally unfriendly component of concrete is the cement. So if you reduce the cement content, you're good to go. Now, there's a lot of really great technologies out there. Many of them have this drawback that they haven't been tested at the concrete scale. So we have a lot to learn about how these technologies work, what is their chemistry, what is their material science, what is their engineering. And for the most part, I work somewhere at the intersection of these three topics. So one very obvious question that everyone asks is, okay, that CO2 is not really key. I mean, that CO2 is not doing anything, right? If we just need to form a calcium oxide in the melt, can't we replace that limestone with something else? And that's a very valid question. I'll let you think about it. I'll address it a little bit later, but I think it's an interesting thought experiment. So I want to cover these, which I'm going to call standard methods. By standard methods, I mean there isn't any major research or development need here. These are all very, very well understood in the lab. They've been studied to death over the last 60 years or something. But implementation maybe is not quite there yet. So some of these include, as we mentioned, use of PLC, which is the Portland limestone cement. So just replacing 5 to 15% of the limestone instead of heating it up. If you add it at the end, that reduces the emissions by about 10%. There's really no change in performance. A major technology is the use of cement replacements. These are known as supplementary cementitious materials. In principle and in practice, it's possible to replace about 60% of the cement with supplementary cementitious materials. Most of these materials have emissions at the most about 20% of cement. So again, you get a substantial reduction here, up to 40-50%. And the nice thing about using these supplementary cementitious materials is they improve the long-term durability or the long-term performance. But there is a little drawback in that your early strength is reduced. There is, interestingly enough, you think concrete is all engineering, but actually a lot of nice things can be done in concrete if you're like Snape and you know your chemistry. So this is chemical admixtures. A lot of these are large-size organic molecules that act as dispersants. They could also be other ones which act as grinding aids, etc. So strategic use of these various chemical admixtures can again reduce cement by another 10%. And typically, these dispersing admixtures, for example, have positive impacts on the long-term concrete properties as well. So concrete is essentially, filling in space. So what you do, if you think about a jar where you put in big stones, and smaller particles, you can actually get really high particle packing and densities. And that's essentially how concrete is, where you put a bunch of big stones, right, the aggregates, then the sand, and then you want to minimize the fraction that you put in cement and water because that's the most expensive part, right? So by looking at particle packing or gradation algorithms, you could probably, again, reduce the cement content by 10%. This also, on the whole, makes the concrete more watertight, so that improves durability as well. Now, if you combine all of these, you've already reduced a significant portion of the emissions without doing any fancy R&D, by just using technologies that exist right now. Unfortunately, a lot of folks are not doing these yet, and there are some barriers which are not research barriers, but are very practical implementation barriers that prevent this. And one of the most obvious barriers, which I do want to mention, is just education. A lot of the folks who work on cement and concrete don't necessarily understand these because they've been doing the same stuff for many, many years and they don't want to change, etc. So simply educating the people who are actually making the cement and concrete can go a long way in minimizing the emissions. There's one more issue. So in theory and practice are the same, but in practice they are not. So unfortunately, what happens is that a lot of times there are very clear guidelines to be followed. This could be designs, codes, whatever, in making concrete. people don't necessarily follow those guidelines, right? For whatever reason. Also, a lot of times things are over-designed. Over-design in simple terms is that if you need something this thick for the structure to be stable, just because you're not sure, you make it this thick. Now, there is something called a factor of safety where, just having the bare minimum is not enough. You want to have maybe 10% more. But if you have 3% more, I mean, that makes it really unreasonable. And again, people do this very, very often as well. These two are probably pretty big problems, but the biggest problem is the third one, which is regular maintenance. So I get asked this question pretty often. Hey, the ancient Romans or Egyptians, they made pyramids, they made ancient concrete, that has lasted 2,000 years. Why can you not make a bridge that lasts 50 years, right? So this is, again, something I ask students to think about in my grad classes. A number of assumptions made, which make this sort of comparison misleading. But the point is, a lot of our bridges or other infrastructure is in bad condition because we make it. And then for the most part, we don't look at it, or we look at it once every 15 years. And this has had very, very regular, awful negative things happening. As an example, we've had building failures in Florida, which have had fatalities associated with them. So regular maintenance of concrete infrastructure is incredibly important. But again, we lack manpower, we lack infrastructure funding and resources to do some of these things. So all of these, there's really no challenge here, at least from an R&D point of view. So we should do these, and a lot of the work that we do is in kind of educating people to not be afraid of these technologies, right? So now let's go on and move towards some actual R&D questions. So one of the materials that I'll talk about quite a lot are supplementary cementitious materials. So these are finely ground calcium aluminosilicates, okay? And these are one of the keys to reduce the CO2 emissions of cement or concrete. So supplementary cementitious materials are typically industrial byproducts, okay? There are some really, really interesting materials that are put in the box there. But apart from them, many of them are available in volumes that are orders of magnitude less than cement, which means there can only be a local solution, but not a global solution. So things that work at a global scale in kind of replacing cement are really limestone, tailings, fillers, which are quarry fines, essentially fines that you get from quarrying operations, and clays or calcined clays. These are the only materials that are available in billions of tons of years sort of volumes. So essentially, what these supplementary cementitious materials are doing is, over the long term in concrete, they react. They consume calcium hydroxide to give calcium silicate hydrate. And again, this kind of makes the concrete more watertight. So it improves the concrete durability, what I have in bold there. They also can improve fresh properties. They can improve later age strength. They can reduce the concrete, but these are probably not the major reasons they're used. And the other major thing is that most of these materials will have very low CO2 emissions, especially if they're industrial byproducts. So they reduce very significantly the CO2 impact. At least till 20 years ago, nobody cared about the CO2 impact of, maybe 30 years ago, nobody cared about the CO2 impact. So they were primarily used for durability. Now the CO2 impact is probably as important as the durability. So the most commonly used ones are fly ash, slag, and silica fume. These are byproducts of coal or steel or iron making. So one of the major issues has been that we're kind of running out of our standard fly ash or slag, or in good qualities. So a major thrust of my research is in identifying new or novel supplementary cementitious materials. We need to identify them, we need to characterize them, and they ultimately need to go and be used in concrete to reduce the CO2 emissions. So the most promising materials, calcined clays are one of them. And I'll talk a little bit about calcined clays, natural pozzolans, reclaimed fly ashes. And these are materials that can be used with relatively lesser amounts of processing. It's not zero, they need to be processed somewhat, but compared to some of the other technologies that I'm talking about, I'd say that there's lesser energy in the processing. So the second part, I'll talk about some technologies, and I'll really put a little bit of focus on them. These are what I would call technologies where you need to do a little bit of processing. These are thermal, these are mechanochemical, and these are enforced carbonation techniques. And primarily the use of these is to take materials like fillers and tailings, which are not reactive, and to largely because they're crystalline, and basically increase their depolymerization or disorder to an extent which makes this material reactive. So, I mean, in the simplest of terms, it's just putting in a lot of energy into the material. So we talked about reactivity. What's reactivity and why is it important? So the reason why, so cements react with water. Cements reacts with water very fast and very nicely. So if you take the cement out and you replace it with 40% of a material that doesn't react, that doesn't do anything, you expect a 40% reduction in performance, right? On the other hand, supplementary cementitious materials or SCMs, they do something. They actually have other reactions. They're not the same as the cement reactions. But because of that, if you put 40% of an SCM, the strength reduction is not 40%. In fact, at later ages, it's probably closer to 10 or 15%. At early ages, it's a little higher. So essentially, these supplementary cementitious materials, as I mentioned, for the most part, are amorphous calcium aluminosilicates. They're now putting them at high pH. So a lot of people are surprised by this, but traditional cement pH is about 13, okay? So you probably should not do this, but if you want, you can look up cement or concrete burn. It's pretty nasty. Concrete will kind of eat into your skin if you're exposed to it for several hours and you don't wash it. It doesn't really happen in any, it doesn't really happen in the US, but in some poor countries where there's really not knowledge, this can happen. It's really an awful thing. But anyway, concrete has very, very high pH, right? So pH 13.5, silicate glasses will dissolve, right? So that's the idea. So these pozzolanic SCMs, that's the first class of SCMs. They react with calcium hydroxide. Largely, they're low calcium materials. At high pH, they react with calcium hydroxide, and then they form CSH. CSH is calcium silicate hydrate. This is the glue of concrete. This is what holds concrete together. And then the second category is latent hydraulic SCMs. These are typically calcium-rich materials. So they're disordered enough or reactive enough in terms of the phases they have that they actually react directly with water to form calcium silicate hydrate. At high pH, they do not need CH. CH is calcium hydroxide. They can react with the calcium hydroxide, but they don't need it. And then finally, there's a third class of materials. Limestone is a great example that are known as inert fillers. Mine tailings are also a good example of inert fillers. These are generally highly crystalline, highly stable. They don't really react with water or calcium hydroxide. They can have some other reactions in concrete, but for the most part, they can be considered to be pretty inert. So what we have developed is what we call the modified R3 test for rapid reactivity determination. So basically, it's just to say, hey, how reactive are these materials? And the more reactive a material, the more strength you're going to get in the simplest terms. It's actually linked a little better to durability than to strength, but we don't have to get into that here. So this test is really very simple. You take calcium hydroxide to SCMs in a 3:1 ratio. You put in a 0.9 liquid to solid ratio. You have half a molar of potassium hydroxide. And then you run isothermal calorimetry, which is just a measure of heat release at 50 C for 3 or 10 days. And then optionally, if you want to measure the amount of calcium hydroxide that's consumed in the reaction, you can run a thermogravimetric analysis at 3 or 10 days. So from a lot of testing, we've kind of found, or it's a bit subjective, but we state that if a material has more than 100 joule per gram of heat release, it can be considered reactive. Anything less than that is not really reactive. So with that in mind, let's consider some of the technologies and now SCMs. So the first thing is limestone calcine clay. So the idea is to use 50%, is to replace 50% of the cement with a mixture of limestone and calcine clay. And I mean, the volumes of limestone and kaolitic clays available are billions of tons per year if you want to get them out. So the technology is easily scalable. Low and mid-range kaolitic clays are ideal for this purpose. We're talking about kaolin content somewhere from 30% to anything higher than that. Illitic and other clays could also work, but it's a little harder and you need to do a few other things. And ultimately, for the most part, this technology, you make concrete which performs almost exactly the same as normal Portland cement concrete. The major difference, as you can see on the graph on the right, is probably the one-day performance, where strength at 1 day actually does reduce. You almost pick it up already at 3 days. So yeah, there's a little bit of a concern with the 1 day strength. Almost everything else, there's hundreds of papers on this. They have shown that you get really nice durable concrete with such a technology. So most of the applications so far have been in India and Latin America. I I'm almost certain this technology is going to be adapted pretty soon into the US. A lot of cement and concrete companies are looking at it very seriously. And there's really zero R&D challenges. All the challenges that are here are extremely applied and I mean, basically the thing is, if you give a cement company about $70 million, maybe something like that, they're happy to make this conversion. But $70 million and increased OPEX is a little bit of an investment, but I believe the technology will come. And in terms of emissions, I mean, there's a bunch of calculations, but about 40%, a little bit here and there, emissions can be reduced by using this sort of technology. Now, let's look at thermal activation. So you can take a mine tailing, or you can take a basaltic fine. So fines, these are crystalline materials. And essentially, if you put in a lot of energy into them, that is, if you heat them to very high temperatures, and then if you rapidly cool them, they become amorphized. So the disorder increases tremendously. So you've taken the inert materials and then made it reactive. So this is some data from one of my students where we've done this with basaltic fines. We've done this with some blends as well. And essentially, it shows that if you go over 1200, you consistently get reactive materials. Now, why is this important? This is important because we have basalts or mine tailings, many millions, if not billions of tons of these materials available. And to a large extent, because we don't necessarily have high volume applications that can generate some revenue, they're just landfill. So you get the materials out of the landfill and you make a product that has some use and some value. Maybe these products are something that could be sold at $150 per ton, etc. Process is not zero CO2. Obviously, there is some CO2 associated with it, but it's significantly lower than cement. And if you're running out of SCMs, you don't really have an option. So what is happening? Well, at high enough temperatures, you get bulk melting and subsequent amorphization. We've confirmed this using XRD and FTIR, and you can kind of see in the XRD curves that beyond a certain point, all the peaks vanish. FTIR also shows peak broadening. And the reactivity is generally similar to fly ash or natural pozzolans. Most of our work has focused on low kaolinitic clays and basaltic fines. And we find in terms of temperatures that the clays, 700 is enough for clays. Clays is not really melting, it's something else which we won't really get into the details of. For these fillers or basaltic materials, we found this temperature melting or really activation temperature to be about 1200. And then we also synthesized pure calcium aluminosilicate glasses. The pure calcium aluminosilicate glasses are only meant to be a model system. We're not suggesting to anyone to heat up, materials at 1600 to synthesize them, but they're a useful model system for understanding some of what is going on. So what are the unanswered questions here? So this is a very, it's not an idea that a lot of people have done a lot of work on. There's not a lot of research and data available. What is well known is if the temperature is high enough, it works just fine, right? Now, can you reduce this temperature? Really, heating up something to 1200 Celsius is not optimal. So can you make it lower? So here is some studies from our group, which basically what we've shown is that just for the basaltic fines itself, you have to heat it up to 1200 and cool it to get a reactivity, somewhere appropriate. But if you replace or if you add about 5% to 8% of some material, which I won't tell you what it is, most of you can probably figure out what it is. What happens is that we kind of get the same reactivity, or at least we get more than threshold level reactivity at 800 Celsius, right? So we have now reduced by 400 the melting temperature, and I put melting in quotes because melting in glasses is a little bit complicated, especially in these heterogeneous systems. So the interesting thing here is, again, those of you who know ceramics figure that this is actually very obvious. The challenge is not in reducing the temperature. The challenge is in actually understanding what is happening. What are the mechanisms of the melt itself, right? Are we forming some sort of a core shell structure where only the surface has melted? Is it a homogeneous melt, or is X kind of distributed in random locations and other stuff have come out of the melt? Or is it that only the finest particles, or maybe particles with very, very specific compositions, those have melted? So those are the questions, and we cannot answer those simply by using bulk averaging technologies such as X-ray diffraction or FTIR. this needs a lot more work, very careful SEM, FIB, Raman, and more advanced technologies. So that's something we're working on. Now, how does this sort of technology scale up? So typically what we do in heating this is just put it in a furnace, heat it up, and then open the furnace and quench it rapidly. Nobody does that at industrial scale. Industrial scale calciners are very different. You can think of them almost like a conveyor belt where the temperature is very, very high. So if you're doing that, if you can actually reduce this temperature or put it through, high temperature, expose, melt, grind, repeat that process, then you start to get very, very important synergies. But the only way to actually optimize the process, the only way, in my opinion, to scale it is to understand fundamentally what is happening. So this could be because of the fluxes, or the partial melting, or the cooling. But all this process science needs some nice fundamental research to back it up. So apart from that, there's a couple of other unanswered questions as well. One is blended SEMs. And by blended SEMs, I mean, what happens when you start introducing a source of calcium into the glass? Most of what we've melted has largely been aluminosilicates. There's very little calcium in there. But calcium has very interesting effects on depolymerization, etc. Calcium increases the reactivity quite substantially. So if you put in calcium, we change the properties of the material, but how do we change it? And is the calcium largely, again, going to focus right on the surface, or does it actually penetrate into the bulk of the material? Things like that. And the other thing is that all of these have typically a final grinding step. So in that final grinding step, what happens if you add a little bit of additions to modify the grinding energy, like grinding aids or other dispersants, etc.? Could you actually increase the strength that you get in the concrete? So these are some of the unanswered questions. So all through my presentation, I've named a bunch of startups. It's not an endorsement of the startups, but essentially, I just want to identify some of the folks that are working in this space. Terra CO2 and NVCore are using some sort of a similar technology to what I talked about. And you can certainly go look them up, talk to them, etc. Terra CO2 is actually pretty close to where we are. So if that's what you're interested in, you can do that. Now, the second topic is mechanochemical activation. And mechanochemical activation is putting in enough energy to these crystalline materials to cause a lot of defects or to cause amorphization of the surface. And this comes about because of the friction, because of the impact, because of the high temperature that you have when you smash things together. Most studies in literature use what is known as a planetary ball mill. It's not your conventional ball mill. A conventional ball mill is just this, right? But a planetary ball mill is more, this. I'm doing a bad job of that, but hopefully the figure has a better job. Basically, I mean, there's a counter rotation, and this actually causes a lot of tumbling action, a lot of heat, etc. So pretty high energy, and also, I mean, typical ball mills, for those of you who are aware, rarely go over 100 RPM. These go 400. I've seen higher ones as well, but so the RPMs are about 4 times higher. So fillers can be activated essentially by high energy grinding as well. We've looked at a lot of basaltic fines. We've looked at mine tailings. We've looked at clays as well. And we've actually demonstrated mechanochemical activation for 10 plus materials. Again, you get similar reactivity to fly ash or natural pozzolans. And here, the phenomenology is a little bit different. So we get increased fineness, right? We also get amorphization. But this amorphization seems to be very different from the bulk melting case, where it only really seems to be at the surface, right? But also it seems to be very, very phase specific. And this probably has to do with original fineness, which original particle size, things like that. So the fundamental question here for this, but also for a lot of other technologies and efforts that I'll talk about, are how do the precursor properties, I use precursor kind of loosely, the chemists will probably shout at me, but how do the precursor properties influence the processing parameters, and the process material itself, right? So it's essentially elucidating the processing structure property relationships in these materials, but there's a very, very, very strong effect of the precursor properties in these relationships. So this is not really a very well understood process, at least for cement-based materials. There's many questions. I actually haven't seen almost any concrete studies on something like this. Most of it is looking at small batches, small scale, hundreds of grams of stuff. And by the way, just so you know, I get people calling me all the time and saying, hey, look, we have 20 grams of material. Can you make concrete with that and do some testing? And the answer is no. You're not going to do any concrete testing unless you probably have at least 10 pounds, but probably closer to 40 pounds of material. That's probably the minimum amount you need to actually do any concrete testing. So you can have the nicest technology in the world, but if you're only manufacturing a few grams of it, concrete testing is some time away, right? So for this technology, for example, we can't really make concrete because we only really make about 200 grams every 15 minutes. So, if we keep on, if that's all we do, then we'll make some concrete. But so far, we haven't even made concrete, which is similar to what most of the others are doing or not doing. So, as I mentioned to you, we're getting some sort of surface amorphization. So determining the depth of that amorphized layer is actually very interesting. And what controls that layer. As with every milling process, there is agglomeration question. So limiting that agglomeration, perhaps by using grinding aids, is of interest. The other interesting thing is, hey, during this process, can you bubble in CO2 or can you carbonate at the same time? That's also an interesting question. And then there's also the question of calcium. So as we pointed out, calcium increases the reactivity of these materials quite a bit. So if you add a calcium source, is the calcium going to get into the surface? And are you going to get very, very reactive material? Could this be a way of making cement? So again, as far as I know, no one has answered these questions. The effect of calcium on mechanochemical activation is unknown. To answer a lot of these questions, we need to do some fundamental experiments, but also multi-scale modeling is needed. And we actually get some very interesting effects. So I call this parting the Red Sea. So essentially what happens is that in many cases, we have an original particle size distribution that looks something like this. After mechanochemical activation, we get a bunch of very fine particles, but then we get a bunch of very, very, very coarse particles as well. So this is interesting because presumably that right is agglomeration. And we've tried a bunch of things, but it doesn't seem to really go away. And it could be basically because you have maybe almost some sort of a sintering effect because the temperatures do go high. Or we've looked at the electron microscope, and essentially what you see is that you see large particles, but they're not that large. The problem is it seems to be a large particle, and then there's a bunch of small particles stuck to it, but then there's another large particle also stuck to it, right? Now, how easy or hard are these particles to, disperse would have a major impact, because to a certain extent, maybe that's exactly what you want, because if initially that's the state of the particles, then you get an improvement in the workability. But then later on, if they actually do dissolve, or the surface area is high enough, okay, we actually then have an advantageous situation. In fact, in several of these cases, we've seen that the median particle size increases and the surface area increases at the same time. So some interesting synergies here that need to be solved. So now the next topic I want to talk about, and the first section was really talking about processing of SEMs, etc. The second is about enforced carbonation or CO2 uptake. And somewhere right in between is going to be a processing technique for SEMs using CO2. So all concrete carbonates, it's pretty inevitable. And if you think about the manufacturing process, right, you put in a lot of energy to get the CO2 out, some of it is ultimately going to come back in. That is pretty obvious. The process is generally pretty slow and is pretty limited. Calcium and moisture are key to this process. There's been many, many papers that discuss what this uptake comes out to. The ones that I've seen generally agree that about 10% of the total CO2 emissions that you make from concrete can be regained over 30 to 50 years simply by doing nothing, right? You just have the concrete, it's slowly sorbing the carbon. It's not sorbing a great amount, but because there's, I don't know, 300 billion tons of concrete out there, it's going to, it's gonna keep on taking in carbon. Now, there are many, 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 many ways of mineralizing carbon in concrete. For the most part, the material you form is calcium carbonate. There are many cases where you form magnesium carbonate. I'm not really going to discuss that, but magnesium silicates are very interesting as well. It's not something I've worked on myself. But basically, when you do the carbonation, it could be completely dry. You could have a little bit of water, or you could almost do it in a steady state. Pressure and temperature can be greatly varied. The purity and the concentration of CO2 can be greatly varied as well. You see anywhere from 1% of CO2. Remember, normal concentration of CO2 is 400 ppm, to anywhere from people using 80, 90% of CO2, which is pretty scary. So anyway, if you were ever interested in how much CO2 concrete can uptake, The answer is depending on everything, somewhere from 1 to 25%, which I understand is a pretty broad range, but we'll dig down a little bit into it. And then you can actually process a lot of different materials. You can just take the fillers or SCMs, right? These aluminosilicates or calcium aluminosilicates. You can expose them to CO2. Or you can take recycled concrete aggregate. So let's say one of the buildings nearby was demolished, right? You make concrete out of it. You can carbonate that. And then there's concrete products like blocks or bricks or pavers, etc. And then, of course, you can also push CO2 into fresh concrete, hardened concrete, or hardening concrete. So all of these are possible. Now, the first technology is enforced carbonation of fillers or supplementary cementitious. So the same materials that I talked about, like fly ash, for example, you could just take the fly ash as is, just in a powder form, and expose it to CO2, and it will uptake some amount of CO2. The key there to having a high CO2 uptake is to have high calcium and mineralization. But of course, I mean, it needs to be in a form that will actually react, because if you just take calcium carbonate and expose it to CO2 without doing anything else, absolutely nothing will happen, right? But if you take these high calcium and magnesium materials, if the calcium is in, as an example, calcium oxide or calcium hydroxide or calcium silicate hydrate gel, they will carbonate. I've seen studies in wet, moist, and dry conditions. But the dry typically is combined with some sort of a milling or grinding process as well, like I've described earlier. So the precursor and processing heavily influence the CO2 uptake. Anywhere from 1 to 25% is possible. And also, at least in some cases, remember we talked about supplementary cementitious material reactivity. It does seem possible that after the carbonation, the reactivity increases a little bit. And this could be because in some cases you form aluminosilicate gel, which, I mean, essentially it's amorphous silica or amorphous aluminosilicates. That's pretty reactive. Calcium carbonate also has some reactions in concrete, which makes it useful. So it could also be just that, your original SCM phases are reacting. So how does this look like? So if you take a fly ash, right? So this is basically the fly ash with 1 day. This is the fly ash with 3 day. And then this is the fly ash with just the mixed water. So typically calcium carbonate decomposes at about 600 Celsius, right? There's a lot of variation in that. You see that the original material already has maybe a little bit of a peak here. Maybe it's an artifact, it's really very small, or maybe there's a little bit, right? And then at 1 day, this peak increases, right? As you can see here. And then at 3 days, the peak increases significantly. But also, this is a little interesting because you almost see 2 different peaks here. So presumably, we formed 2 different kinds of carbonate. Maybe it's magnesium carbonate, or maybe it's some sort of amorphous calcium carbonate. Either way, you can actually calculate what the CO2 uptake is. And people are surprised because they look, oh, this is a huge drop. I mean, it actually really isn't if you take a look at the numbers. This is only equating to about a 3% CO2 uptake. So there are obvious questions, right? Is it worth it to do this for 3% CO2 uptake? Maybe, maybe not. On the other hand, this is a recycled cement paste. By recycled cement paste, I mean you mix cement and water, okay? And then once it hardens, you grind it to some sort of a, 15, 20, D50, and then you expose it to CO2. So this one has a lot higher CO2 uptake. So this is the original cement paste, and this is 1 or 3 days. Doesn't really make much of a difference. You can see that there's a massive amount of CO2. So I think it's 65, 25. It's about 50% of calcium carbonate in that system. The CO2 uptake comes out to about 22%. So a very high amount of CO2 uptake. This is fantastic. People would love 22% CO2 uptake. Why don't we do this? Because this is really a synthetic system. Nobody does synthetic cement paste or recycled cement paste. But we kind of use this as, this is almost our end case where we really know that almost nothing we do, short of putting in a slurry of calcium hydroxide, will show these levels of uptake numbers, at least for cementitious materials. So this is pretty consistent with literature. There's a couple of studies on this, but this seems to be about the maximum that we can get. But for most realistic materials, it's actually 3 to 10%, right? So quantifying the CO2 uptake is not that challenging. Although, again, trying to explain, why there are peaks at 400 is, you can actually see that, this peak is overlapping with the calcium hydroxide peak. It overlaps with a couple of other things as well. So there is some importance in the measurement. There is, better techniques, including evolved gas, etc., could improve the exact amount. But I mean, maybe it's not 22%, maybe it's 20%, right? We can get to that. That's not the major challenge. The major challenge is this. So we know what the carbonatable phases are. You can put together a list of all the phases in cement and concrete that are carbonatable. But there's a lot of evidence that for the phases, we sometimes only get 20% of the theoretical, in some it's a little higher, in some it's a little lower. So we actually don't carbonate anywhere near the full capacity. Why is that? That's a big question. Then the calcium aluminosilicate glasses, the synthetic glasses, which are a model system, nobody has studied those glasses for their carbonation. And that's actually very interesting because they are fundamentally simple model systems to explain what's happening. What are the optimum conditions for doing this? Is any range of possible optimum conditions? The kinetics of carbonation are not all that well understood. And for me, the biggest question is basically this. So what does the phase assemblage or the morphology look like after the process? And by the way, it doesn't look anything like that, that's for sure. But essentially, you're forming calcium carbonate, right? Is this just a very thin layer of calcium carbonate, or is it a pretty thick layer? Is this a very dense layer, which is causing, basically at some point just to stop, right? Does this start off at some kind of a defect? Or is it only the most prone phases to carbonation that are reacting? So a lot of these questions are not answered. Again, bulk techniques like XRD, TGA, FTIR will only get you so far. So you kind of need to use XPS, XCT may or may not be good enough, not sure about the resolution, but FIB, XCT, Raman, etc. The technology is needed, maybe even TEM, to really understand this depth of carbonation kind of phenomenon and how that varies, and what implications that has to the CO2 uptake. So we've done a little bit of work. I mean, most of the materials, as I said, have 5 to 10%. We are trying to understand a little bit more now about the phases. The problem is, I mean, if you think about it, quantitative XRD is a fantastic technique, and it'll tell you exactly what's happening. But you already, in many of these systems, you have 7 different phases. After carbonation, you form 2 more phases, right? Most of these techniques don't work when you have 9 phases which are heterogeneously distributed. So that's one of the reasons why we are interested in looking at pure phase glasses. So you can also take the recycled concrete aggregate and carbonate them. And this has been studied for a number of years. There are really no R&D challenges. You can take any sort of recycled concrete aggregate. You can also take lightweight aggregate. Almost everyone just does twice carbonation, where you add a little bit of water. The exposure duration is few hours to a few days. For the most part, the CO2 uptake in this, maybe about 1%, 1.5%. Others have claimed higher numbers. So, and some are speaking very high numbers. So I don't know how that would be possible. So, in recycled concrete aggregates, you can think of aggregate with a thin core of cement paste. So maybe they do some sort of a separation technology where they remove all the cement paste, right? And then they separate out the aggregates, and then they expose the cement paste to CO2. I guess that could be possible. But anyway, so those sort of more applied questions, there's a few of them. But the advantage of this, even though the uptake is very low, is that recycled concrete aggregates have not the best properties. They absorb a lot of water. They're weak. They're weak to strength, etc. By carbonating them, a lot of data has shown that you improve the properties, you improve the strength of the concrete, you increase you increase the water tightness of the concrete, etc. And it's important because, of course, I mean, 80% of your concrete is still the aggregates. So if 80% of it has 1%, that's still a pretty decent number. So most of the questions here revolve around scalability. There's also CO2 pure products, CO2 pure concrete products. So one way of doing this is just to take your normal concrete, fresh concrete, and then just inject a blast of CO2 into this. The uptake in this case is really pretty low. I mean, it's maybe 1%, maybe even less than that. And the claim from the startups has been that you can actually reduce your cement content by about 5% because of the formation of nano calcium carbonate phases without actually reducing the concrete performance. So the reduction here is not really so much because, or in the reduction of emissions, is not so much because of CO2 uptake, it's rather because of reduction of cement content. So the second kind of technology is as the concrete is hardening, you inject CO2 into that. And this could be concrete, bricks, blocks, pavers, other. Most of these cases, if you're using just standard concrete materials, again, the uptake is very low, it's less than 1%. But if you're replacing standard concrete materials with elastomeric, carbonatable materials, for example, or steel slags or recycled concrete materials, etc. In this case, people have actually reported higher CO2 uptakes, in some cases up to 15%. For the most part, unless you have like 15% CO2 uptake, the performance is pretty similar to conventional concrete products. You don't really need to make a whole bunch of changes. And as the CO2 goes in and forms calcium carbonate, water is expelled as well. So some sort of water recovery may be possible also. These are very different concretes from conventional. So combinations with like non-corrosive reinforcements, etc., could be very interesting. These first are generally understood. There's some questions there and a lot of questions about optimization and scalability. So a couple of the questions here that are interesting. So you can take a concrete block, CMUs. I think everyone has seen concrete masonry units. And these guys carbonate very rapidly, okay? We've actually been able to carbonate some of them, thick sections, by the way, in 8 hours, right? This is fantastic. It's uptaking a lot of CO2, right? Well, maybe not. So that test is basically a phenolphthalein dye test. And essentially, it's a pH indicator, right? So if the white portion is basically telling you that the concrete has carbonated or the pH has dropped really. So the CO2 has gotten in. That is correct. But the thing is, the amount of CO2 we couldn't even measure. I mean, 1% uptake is a different story, but this was not even detectable how much CO2 it was. And it has as much to do with the limitations of some of the techniques that they're using. But very, very, very small uptake. So, I mean, is it possible to increase both the depth and the CO2 uptake? Maybe you'd have to use a lot of calcium-bearing materials. And some people are working on that, primarily using like steel slags. And then there's actually a major question that revolves around the measurement itself, right? So, and NIST is doing a lot of this work, far more than me. But the question is, I mean, looking at the concrete and saying, hey, it's not pink, it's carbonated, is something people would have done 200 years ago. So can we do a little bit better? But I mean, we have to still do it rapidly. So maybe embedded sensors are the answer. Maybe you need to do some nice Raman, a lot of questions. And what does that depth actually mean? I mean, have you completely carbonated all the materials that you have? Or is it only 20%? Is it kinetic or diffusion limited? All those questions also. And then at any given point, how do you quantify how much CO2 has gone in, right? Is it PGA, Raman? Mostly people kind of use total carbon, where they essentially take the whole thing and grind it up, and then they take a representative sample to measure it. So again, there's a bunch of questions there. And one of the reasons I really hate using this pink phenolphthalein thing is that there's a bunch of different specimens. I mean, I don't know white versus pink. I mean, you can use image analysis, of course, to kind of get an area extent. But clearly, I mean, it's obvious that there isn't any clear front or any sort of ingress there that you can understand what's happening. So what's happening? So some of the questions there need better techniques, like maybe a Raman to explain. So moving on from carbonation, as I mentioned to you, it's entirely possible to develop completely new cements. All of these systems basically say, hey, look, forget limestone. We're not going to heat any limestone. We're going to do something else. Could be electrochemical, could be chemical, heating, various other processes. So chemical engineers, this is where they shine, right? So you primarily avoid the heating step of the limestone. And most of the folks that do this use calcium silicates, magnesium silicates, aluminosilicates as their raw materials. And this is the wild, wild west where carbon negative is often claimed, CO2 is often claimed. I mean, not a lot of details are available as to what these folks are doing, which is not surprising because when you have technology that could change the world, maybe publishing is not your priority. So if you do want to, you can kind of reverse engineer some of their stuff by looking into the patents. I prefer not to do that, but there are many, many, many people who do that. And you can understand how some of these technologies or whatever will work if you kind of look into the patents. Bottom line is a huge amount of research is into the mechanisms here. Almost nothing is understood about how these materials, I mean, the processing structure, property relationships of these materials are not understood. concrete testing at least is very limited, and in some cases, folks may not even have made enough material to make concrete, right? So I don't know if you've been following the news, but at least a couple of these startups have received certification, which means they can actually, in principle, sell material. So exciting times ahead, right? They could actually be selling their materials. We're making a lot of progress with them, but there are many questions. And philosophically, I always have this question that, hey, I mean, to do this, if you call the new startup Cemex or something, Cementex, it's going to cost $1 billion to build, a completely new plant that's going to make you several million tons of cement a year. Or, as I mentioned to you, to convert any existing cement plant into LC3 is probably about $70 million. So if you put in 1 billion, I mean, the volumes that you're affecting are much greater. So which of these is better? I mean, in reality, we probably have to use both of these technologies. We need to get anywhere to carbon zero, but something like this is important. And then there's also the question of, we struggle to predict the long-term properties of normal concrete, right? How do you predict the long-term properties of these new cements, or rather the concretes made with these new cements? So in case you haven't had enough of approaches, there's actually a lot of other things as well. Luckily for you, I won't get into the details. But people talk about bio-based cements, calcium carbonate cements, and then there's alternative cements like geopolymers, which have been around for a long time, calcium aluminate cements, etc. There's also, carbon capture that people can build into cement plants. Lots and lots is happening. So watch the space, and some news about the world's first cement carbon capture facilities there in case you're interested. Prometheus Materials, by the way, is from CU Boulder, in case that's something you want to check out. All right, so those were all the approaches. And in each of them, I kind of try to highlight the research need, or I kind of dismissed it as, oh, we understand everything. Hopefully we do. But anyway, what else do we need? So I'll only talk about two things. One is model systems and synthesis. A lot of civil engineers run the moment you say synthesis, but for me, in my opinion, this is one of the most important missing pieces here. That is that cements, SCMs, and concretes are incredibly heterogeneous, complicated. Really, nobody wants to study something that has 25 phases or 10 phases in it, right? You get far more fundamental information. Specifically, the processing structure property relationships can be elucidated for properties could be hydration, carbonation, admixture, interaction, organic admixtures, whatever. If you simply, kind of make simple enough model systems. So instead of the cement, halite is actually a very nice model system, or a mixture of halite and tricalcium aluminum and calcium sulfate. Henrik Heinz at CU Boulder has done a little bit of work on this, on such model systems. Cement model systems have received some study. There's far lesser study on SCM model systems. So as I mentioned to you, the calcium aluminum silicate glasses, you can actually synthesize this. The method we use to synthesize is just heat them and cool them. Not trying to mimic industrial practice, but that's how you can synthesize these materials. And then in one of our projects, we synthesized a bunch of materials. I'm not showing you all the data, but essentially we kind of covered the calcium alumina silicate phase diagram, not exactly a phase diagram, but ternary diagram. And then we also started doping it with magnesium and iron. And then we kind of said, hey, what's the reactivity going to look like? So ultimately, we kind of want to do a little bit more than this. This is still ongoing. But essentially, you see a kind of multiple different behaviors where now we're talking about reactivity kinetics, which we did not really talk about. But in a couple of cases, you get slow and sustained, which is, the heat is slowly increasing. In some, you just get rapid increase where it kind of slows down. And then you kind of get a rapid increase, and then which kind of continues as well. So the initial portion is largely controlled by calcium because it has huge effect in polymerizing the glass. The later effect is controlled by the silicon, presumably because if you don't have enough silicon, you're not really forming much of a dissolvable glass in the first place. Obviously, you want to relate this with structural parameters, not just calcium and silicon. And that's something that we are working on. So, and that actually brings me to the second thing, which I think is extremely important, which is modeling. So civil engineers are being maybe a little slow to take to modeling, but you can get an incredible amount of information by using thermodynamic, AIML, or MD and KMC. So increasingly, there's been a good amount of thermodynamic modeling on this, a decent amount of AIML, and a few dedicated researchers who do MD and KMC. But many of them, especially in the last case, the folks doing MD and KMC, molecular dynamics, by the way, and kinetic Monte Carlo, don't necessarily integrate that with experiments because it's not that easy. So then, that sort of interplay and understanding more about the experiments and materials themselves kind of, is scale limited because of MD. One of the things that's really missing is modeling at somewhere between the millimeter scale and the nanometer scale. So the 1 micron or 100 nanometers, that has been a scale where not a lot of work has happened. So this is some of the work that we published recently with one of my colleagues who leads that project, where they're basically looking at calcium aluminosilicate glasses. And this is kind of showing you the coordination number of the AL and how that essentially changes based on where you are in the CAS diagram. And then we kind of try to say, hey, does this at all lead to experiments in any way? And we actually could find a lot of links. I mean, this is still something we were working on to try to make sure that what we have is physical meaning and it's not just, fishing for relationships. But we find, for example, that the isotropic shift measured from NMR seems to have some sort of a strong dependence with simulation-based angle number. So now I want to talk about a little bit of practical considerations. As I've said a few times now, for many of these new approaches, concrete scale testing and durability is really very limited. Oftentimes because startups cannot really manufacture a lot of material. And the other thing is that accelerated testing takes time. And well, accelerated testing is basically increased temperature, right? So you always have to think about the kinetics and thermodynamics that can really go crazy when you start increasing the temperature. So, I mean, if you take an egg and you heat it up at whatever, in a pan, you get an omelet, but if you heat it long and slow, you get a chick. And this is a pretty classic problem that we have in our accelerated experiments where, the findings from the accelerated experiments are not reflective of reality, but you won't know reality unless, you do 30-year experiments. And sometimes these 30-year experiments are very hard to fund. So many new materials are not covered by specifications. So we kind of need to develop specifications, and these specifications need to be performance-based, not prescriptive. And this really holds true for SCMs where it's not there. Unfortunately, specification development takes years because the industry is pretty high inertia and resistant to change. And then we have not talked at all about what happens. A lot of the way that you control concrete properties is by using chemical admixtures. Do any of these new products, how do they integrate with chemical admixtures? And all sorts of other new technologies, fiber reinforced polymers, 3D printing, ultra high performance concrete. These are well understood technologies for concrete that have been very promising. So can you combine all of these low carbon cements or SCMs or carbonated material with these technologies is also of interest. So to kind of summarize, we really need a lot of fundamental interdisciplinary research. Primarily, I think the areas that I would identify with respect to manufactured supplementary cementitious materials and with CO2 is really with thermal mechanochemical activation, CO2 mineralization for this and SCMs and new cements. For others, I think the research needs are a little bit more applied. And really, a lot of this has to come from chemists, from material scientists, and chemical engineers as well. A lot of this work needs to focus on model systems and on modeling approaches. Durability and long-term tests are needed. And then a very, very important question is, maybe this technology is wonderful, but maybe it doesn't scale at all. And maybe, you increase the price by way too much, or maybe, over the life cycle, your emissions increase. So quantifying these at the system scale is extremely important. In general, there's a lot of challenges with accurate measurement of quantification of carbon in these heterogeneous systems. Specs and specification changes are also needed. Education is just as important to get. We already talked about how education was a barrier even for existing technologies. As you can imagine, for new technologies, it's even more important. And then synergies and integration with other technologies is not understood. And this has absolutely nothing to do with any of this material. It's just that we often have middle and high school students or undergrads that come to us, and then we have them play around and make small concrete Star Wars or Halloween pieces. And this is kind of our way of educating really, really very young folks about concrete. Maybe some of them decide, oh, you know what, this is what we're going to do. Fingers crossed. So with that, I'd like to thank all my sponsors for making some of this research happen, and the grad students and the rest of the research team for actually doing all the work. And I'd like to thank you. You is the symbol of the U. It's not that I can't spell, but anyway, I'd like to thank you very much for the invitation and for the amazing hospitality that you've shown. Thank you very much.